from ANU, Canberra, who will speak on operator algebras in rigid C-star tensor categories.
All right. Is this on? Yep. Okay. So first, I'd like to thank the organizers for inviting me to speak. And so today I'm going to talk about operator algebras in rigid C-star tensor categories. So to begin, I should probably define a rigid C-star tensor category. And there's one definition that I usually give to operator algebras, and there's another one that I give to category theory folks. And we have an interesting mix in the crowd, so I'm going to give neither definition, and in fact not give a definition at all. But I'm just going to talk about some examples. And you can pick your favorite example from this list. Hopefully you'll be familiar with at least one of them, and you can think of that as a rigid C-star tensor category. So examples of rigid C-star tensor categories. So the first one is the tensor category of finite dimensional Hilbert spaces. Okay, so in some sense this is the trivial rigid C-star tensor category. It has one simple object, right, the scalars, and every object in this category, so every finite dimensional Hilbert space, is isomorphic to a direct sum of that one simple object. You can take tensor products of these things, and if you have morphisms between Hilbert spaces, you can take tensor products of those. And so this is kind of the motivating example, perhaps, if you will, in some sense. The second one is going to be Hilbert FD of G, where G is a discrete group. Okay, so pick your favorite discrete group. Hilbert FD of G is the category of G-graded finite dimensional Hilbert spaces. So objects will be finite dimensional Hilbert spaces that have this G grading, and everything works like before, except the morphisms in this category have to send G-graded components to G-graded components. And then the tensor product works if you have a Hilbert space that's homogeneously graded by an element G and another one by H. You take their tensor product and the grading shifts. So you take the tensor product of the corresponding Hilbert spaces and you shift the grading. And this is kind of a nice tensor category that really just is encoding the group G in the tensor category framework. So earlier this morning you heard Surin talk about the standard invariants are kind of group-like objects. And in some sense, if G is a group, you can construct one of these things, a tensor category, which really is just has the information of the group in some sense. Okay, and then the third example, which actually includes this example but is more general, is rep G, where G is a compact quantum group. Compact, I'll just quantum group in the sense of Woronowicz. And so, if you don't know what that is, just take G, a compact group, and look at its representations. Most people are familiar with the representation theory of SU2, for example. So you can think of that. And then, fourthly, and this example is universal, you can take the category of bifinite index bimodules of a 2-1 factor. And this is a category that Surin mentioned this morning as a nice example of a rigid C-star tensor category. And every rigid C-star tensor category can be realized as a full subcategory of this for some 2-1 factor. And fifthly, and so this you might take as a definition if you happen to know what a unitary fusion category is. But unitary fusion cat. But I'm going to allow the set of isomorphism classes of irreducibles to be infinite. But so possibly IRC equals infinity. Okay, and so usually the word fusion category in the literature means there's only finitely many isomorphism classes of simple objects, but that's kind of a silly restriction. And I am proposing that fusion category should be generalized to be this, and if you want the other one, you should say finite fusion category. So put me on the record for saying that. I think that would make a lot of statements more convenient. We wouldn't have to call these rigid C-star tensor categories anymore. We could call them unitary fusion categories. It sounds much better. Okay, but so the whole point is that why do people study tensor categories? Well, the idea is that things that can be axiomatized in terms of multilinear maps actually make sense in an arbitrary tensor category. So things axiomatized by multilinear maps makes sense in any tensor category. And indeed, you might have some kind of object that is not an associative algebra, for example, but is an associative algebra object in some other tensor category. And so, in particular, so associative algebra, I should say, is such a thing. So associative algebra, what is it? Well, an ordinary associative algebra is just a vector space, so it's an object in vector spaces, and you have a map, M, from A tensor A to A. And so here I'm going to introduce the string diagram notation for tensor categories. A map from A tensor A to A can be represented by a trivalent vertex in the plane. And here we're meant to think of a picture like this as representing a map from A tensor A back to A. Now, the associativity axiom can be easily seen. One of the reasons you use such a diagrammatic notation, because associativity is a nice picture. Okay, and so what does this mean? This means if I put an element in A in each of these slots, so this means if I put A tensor B in here and I do multiplication to these two, and then I do multiplication with the third component, that should be the same thing as moving the parentheses over, doing multiplication here, and then doing multiplication here, right? So that's what this picture represents, and these pictures make sense in any tensor category. All you need is a notion of a tensor product of morphisms, and this makes perfect sense. Okay? And my associative algebras, I'm always going to assume that they're unital. So I'll put this unital axiom down here. And so what does it mean to be unital? It means I have this map, which I'll call 1, that maps from the scalars into A. And we're meant to think of it as taking the canonical element in the scalars, namely 1, to some element in here, which we'll call 1 sub A. This is the unit of the algebra. And we can represent this graphically by a little string. So empty space in this kind of tensor category framework usually is taken to mean the unit object in your tensor category, which is oftentimes the scalars. And so this is going to represent the map that takes 1 in scalars to 1 in A. And then unitality can just be written this way. So if I do this, this should be equal to this, which should be the same thing as this. So this means if I do 1, so empty space is supposed to represent 1 in C, and I plug in A, and I do the multiplication, I haven't done anything, I just get A back. Okay? And the same thing on the other side. And again, this is something that makes sense in any tensor category. So in any tensor category, we can talk about what a unital algebra object is. Okay? And so let's think a little bit about what unital algebra objects would be in these categories. Okay? So let's take these categories, and I'm going to fib a little, and let's forget about the unitary structure. So let's take each of these categories, at least these first 3, and forget that we're talking about Hilbert spaces, and let's just think finite dimensional vector spaces for each of these. Just because somehow the Hilbert space structure isn't relevant for this. But so in rep G, or no, in Hilb FDG, associative algebra and with a unit is just a G-graded algebra. Just an ordinary associative algebra that happens to have a G grading. Okay? In rep G, and here we'll just think of G as a compact group instead of a quantum group, although this actually makes sense more generally. An associative algebra is and this should be finite dimensional, right? Sorry, because we're at finite dimensional land. Is a finite dimensional algebra where G acts by automorphisms. Okay, well, so that's easy to see because an object is a vector space that carries an action of G, and we're asking that the multiplication map be a G intertwiner. So that's exactly asking that G act by automorphisms. So already we've seen things that are familiar, but what if we look at this category here? So in BIM Fi of n, so we want to add an extra condition here, which I won't tell you what it is, but it's a Q system, which is a notion originally due to Longo. and for those of you in the category business, this is just a kind of unitary Frobenius algebra. But what you get is a finite index subfactor. N inside N. Okay? So already we see that thinking about algebra objects in tensor categories gives us interesting things, and particularly here, this gives us the whole theory of subfactors back. It gives us the theory of subfactors in terms of this tensor category here, is perhaps a better way to say it. Okay, so the whole point of this talk is we want to do operator algebras. And we want a theory of operator algebras that defined for a rigid C-star tensor category in such a way that when we put in the trivial rigid C-star tensor category, we get the whole theory of operator algebras back. So we get C-star algebras and W-star algebras and things like this. Okay, so the first objection, so you might think about this and say, okay, a C-star algebra is an algebra object in the category of vector spaces. It's not in the category of finite dimensional Hilbert spaces, obviously, right? We want to allow infinite things. So how do we reconcile this situation? Well, it turns out there's a, so if you take Hilbert FD, so what you can do is you can forget about the unitary structure, and you end up in this category of finite dimensional vector spaces. Okay, and now there's a categorical construction called the IND construction, which you should think of as a kind of completion where you allow infinite direct sums, but somehow it's even more than that. And we'll talk a little bit more about what that looks like later. But if you complete this, you end up with the category of all vector spaces. Okay? Now, when you're doing operator algebras, you don't just want to talk about algebra objects in a vector space. You want to be able to talk about their interaction with Hilbert spaces, right? The fruitfulness of the theory, and indeed the reason for the name operator algebras is because every C-star and W-star algebra can be realized as bounded operators acting on a Hilbert space. So we also want to have the Hilbert space theory in our picture. Well, it turns out that there's a construction, which I'll call NY-IND, that I believe first appeared, it was introduced by Neshvev and Yamashita, and it's similar to this construction, but it remembers that there was a C-star structure here. And so it completes it, but keeps the fact that it was a C-star category going on. And if you do it to this category, you end up with Hilbert spaces, not finite dimensional. Okay? And operator algebras kind of lives in the interaction between these two things, the theory of operator algebras. Operator algebras. So what we would like to do is have a generalization of this whole picture where we replace Hilbert FD with an arbitrary rigid C-star tensor category. And indeed, we can do that. So C is a rigid C-star tensor category. You can forget the star structure, and you end up with, I'll just call it C again because I don't want to introduce new notation. It's the same category, just forget that there was a star structure there. And again, you do this construction IND, and you get this category. I mean, I suppose you should call it IND C, but to underscore the analogy with this situation, we'll call it VEC. And you can do the Neshvev Yamashita IND, or maybe this one day will be called a C star IND or something like this. And you end up with the category that we'll call Hilb C. And then operator algebras should we should be able to generalize the theory to this situation. Okay? And so that's kind of the goal. That's what I want to do for you guys today. But I'll first, before I go into to what you do and how you actually define a C-star algebra object here, maybe some motivation is in line so that we're not just generalizing for the sake of generalizing. Okay. So some motivation. So analytic properties. And by analytic properties, I mean things like amenability, property T, the Hogarth property, and things that you're familiar with from groups, from their unitary representation theory. They can be defined for, well, in particular, discrete groups, but also discrete quantum groups. For 2-1 factors, as Sarin was talking about earlier, and also for rigid C-star tensor categories. And these are definitions that were introduced about 2 years ago by Popa and Voss. and for rigid C-star tensor categories. And each time that you study these properties, you come up with some definition that kind of makes sense. It mirrors the other definitions that you already had, perhaps for discrete groups, and you go and you prove all these theorems about this, and you study these properties and see what they mean. Well, one way that we can put all of these properties under the same roof, to each of these kind of objects is a canonical W-star algebra object in the appropriate rigid C-star tensor category. So you can define what it means for a W-star algebra object in a tensor category to have property T, say, and it actually agrees with all these notions that were defined in these different situations. So what it does is it allows you to put, from the point of view of analytic properties, you can put rigid C-star tensor categories and discrete quantum groups and even 2-1 factors kind of on the same footing in some sense. And so that's kind of one motivation, and indeed that's how I came to this, is I was thinking about all these different notions and how they were related, and there was this kind of underlying thing that it turned out to be a W-star algebra object. Okay? Another motivation is to study infinite index subfactors, but in particular quasi-regular subfactors. Subfactors from a categorical point of view. From a categorical framework. Categorical POV. Okay, so this goes back to over here, where if you had this category of bifinite index bimodules and you had this Q system, you had a finite index subfactor. Well, it turns out that if you have a sufficiently nice W-star algebra object, and you look at one of those in this category, you get a quasi-regular subfactor. Okay, and there's much more general kinds of W-star algebra objects in this type, but that's one nice class that you can really get your hands on, and you have this nice kind of correspondence there. And this is very much related, this point of view, to the work of Popla, Shatenko, and Voss, where they study tube algebras of quasi-regular inclusions. That's very closely connected to this situation, if you remember from Stefan's lectures last week, for those of you that were here. Okay, and then a third kind of motivation is enriched quantum symmetry. Okay, so in the last couple years, there have been people who have been very interested in studying tensor categories where the Hom spaces, instead of being vector spaces, are actually objects in some other braided pivotal category. And indeed, you can do a theory of planar algebras there. And so one idea is that so just like there was this kind of correspondence between planar algebras and subfactors, there should be some kind of correspondence between enriched planar algebras, or these anchored planar algebras, and something else, some other kind of subfactory type thing. Well, one proposal is to use subfactors, but the factors are now W-star algebra objects in some tensor category, rather than actual W-star algebras. Okay, and so the one idea is that the theory can generalize in that direction. Okay, so that's kind of the third motivation there. So hopefully that's enough motivation for you guys. I mean, for me, it's just enough motivation to be like, whoa, cool, you can do operator algebras in a tensor category? Like, that's enough for me. But hopefully I've convinced at least someone that this might be interesting to think about. Okay? So, so what I'll do is I'll kind of tell you a bit about what these two categories are. Okay, so for people who do category theory, you don't need me to tell you what this is. This is the end category. It just exists, but there's a nice model for VecC. So VecC you can think of as functors from C-op to vector spaces. And the tensor product here will be the Day convolution product. And I won't go into what that is, but yeah, and the morphisms are just natural transformations. Okay, I'm going to give you an operator algebra picture in a second. So if you don't know what I'm talking about, don't worry too much. Hilbert will be the same setup, but you're going to want functors from C-op instead of to vector spaces. Well, we're going to put them in Hilbert spaces. And I don't just want any functors. C had a star structure. Hilbert spaces have a star structure. So I want star functors. So the star operation commutes with these functors. Then I'm going to want, instead of arbitrary natural transformations, I want bounded natural transformations. So natural transformations, they're mapping between Hilbert spaces. The soup should be finite. And then the tensor product, you have to modify Day convolution. So there's some kind of unitary version of Day convolution. And the reason you have to modify it is the tensor product of vector spaces and the tensor product of Hilbert spaces are not exactly the same, right? When you take the tensor product of Hilbert spaces, you have to do kind of an L2 completion. The same story goes on here. There's something a little bit different you have to do, but you can kind of follow your nose if you know how this works, and you can do it here. So for those of you who don't know what the Day convolution is, for example, this is entirely useless. So let me give you an operator algebra picture. So suppose C is realized already as some category of bimodules. Okay, so I just have some collection of bimodules inside the bifinite index bimodules of a 2-1 factor, and it's closed under tensor product and all of these things. Well, this is a nice rigid C-star tensor category. So if I have a sequence of vector spaces, if I have V sub A, so suppose I just have a sequence of arbitrary vector spaces indexed by irreducible objects, some choice of irreducible objects in my category, then I can define an algebraic NN bimodule by taking the vector space direct sum over these irreducibles of V sub A tensor this A, where A was actually an honest bimodule, a Hilbert space bimodule of my 2-1 factor. I can just form this new vector space, and now here I'm thinking of putting VA on as just a multiplicity space. Okay, and I take this direct sum is obviously not a Hilbert space direct sum, but rather just an algebraic direct sum, and this is an algebraic NN bimodule. Okay, and the intertwiners in this category will be just linear maps that, since these are irreducible, they're just going to be given by linear maps between these multiplicity spaces. Okay, and so I can take the category of algebraic NN bimodules that are isomorphic as an NN bimodule to something like this, and that will be my end category. And the tensor product, again, is just going to be the tensor product of these as algebraic bimodules. Okay, where you do, the relative tensor product there. Okay, so that's my big category, and this should be thought of as LettingC. Now, to do Hilbc, you do the exact same sort of thing, but instead of having vector spaces, you have actual Hilbert spaces. And when you do this here, you take the Hilbert space direct sum. And now morphisms in that category should be actual bounded linear maps between the resulting Hilbert spaces. So Hilbc is similar, but you just replace this with Hilbert spaces. Okay, and so that's kind of a picture about what these categories really are. But the kind of categorical model, if you want to do things intrinsically, really the correct way to do it is with end and this ny end. These are kind of invariant and don't depend on your model. Okay, great. So now that we have this notion, we'll take an algebra object in here, and we'll try to figure out some good definitions for what it would mean to be a C-star algebra object. So to do that, first we need to define what a star algebra object should be, right? That's something that's not entirely obvious. So let's see, where do I go? I'll go here, because I already have the algebra axioms written, so I don't have to remind you of that. So let's let A be in vec C, okay? So it's an associative algebra that satisfies all these properties. Okay, so what I want to do now is tell you what it would mean to be a star algebra. And this definition might seem a little ad hoc, but actually there's a much more natural definition that I'm not going to tell you because it maybe involves a little too much category theory for the present talk. So, a star structure on A is a family J sub A, and this is going to map from the Homs in my category from A to capital A to A bar. So by this picture, by this box, I'm kind of representing all the possible Homs from A into capital A. Because I guess I didn't even mention this point, but one of the critical features of these categories is that C embeds inside here in both of these times. Okay, so I can think of this category, really I can think of these categories as just big tensor categories that contain C, and somehow the objects are determined up to isomorphisms by their Homs to C. So that's kind of what it means for C to be like, it's a completion of C in the sense that it's a big, nice tensor category, but really everything is determined by C. So in that vein, we're going to define a star structure in terms of a bunch of maps on the Hom spaces from A to capital A, where A is an object in C. So A can be any object in C. Okay, so it's a family of maps that go from here to here, and by A bar I mean the dual object of A. So that's something that rigid C-star tensor categories have. Every object has a dual, and so this will be a family of maps, conjugate linear maps. So these are vector spaces, so I can talk about what it means to be a conjugate linear map between vector spaces, and they should satisfy the following properties. So if I do JA bar composed with JA, so this maps from, so JA maps from A to lowercase a capital A to lowercase a bar to capital A, and if I do this map, I'll end up back in Homs from A to A, in some sense. I mean literally. And so this should be the identity, right? So this is just like the property of a star structure on an associative algebra. You need it to be an involution, okay? And then this next property, let's see if I can do this. So it should satisfy this. Okay, that was a workout. So JC should be equal to this, where now I need to tell you what this means, where alpha bar star equals alpha, where I've rotated everything, and then I've taken the star. Okay, so this is the first place where you use the fact that C itself is a rigid C-star tensor category. So I can tell you what it means to rotate a morphism, and I can take the star of that morphism. Where in VecC you can't actually do that, right? VecC itself doesn't have anything. And I should mention that really what's happening is that there's the C has a structure of what's called an involutive category. And that's really what you need to make all this work, but I'm going to avoid telling you what that is.
Easier without the alphas underneath if you just do JAB.
But you need the alphas for the naturality condition. You could put it in two conditions, or you can put it in one, and have a wonderful picture on the chalkboard for posterity, because they're recording. Okay, great. So this is kind of the condition, and you can see what's happening is I've kind of switched the order of multiplication. If you somehow think of this operation as multiplying these Homs, I've switched the order of multiplication, but there's this kind of naturality condition that you have to have with respect to this rotating star structure on C, okay? And this rotating star structure is really an instance of an involutive structure, which I believe was introduced by Dave Penneys and Andre Enriquez. And so that's it. That's what a star algebra is. Okay, so you guys are with me? We have this nice notion of a star algebra. So what do we do with a star algebra? So if you have an algebra, even an algebra object in a tensor category, I mean, you want this thing to, you're thinking of this thing like an associative algebra, and maybe you're thinking of it like a C-graded associative algebra or something like this. It's not an actual associative algebra is the problem. So it's hard to do things to directly generalize a lot of the C-star axioms that you would want to try to axiomatize. But algebra objects in tensor categories have actual categories associated to them. Namely, I can take the category of A modules, and this will be an honest-to-God category. And it turns out that if I put a star structure on my algebra, then the category of projective A modules, or even the category of free A modules, will actually be a star category. So let me just tell you what this category is. So define M sub A. So A is an associative star algebra. The objects are just going to be the objects of C. Okay. So yeah, I just have the object of C itself, which is the rigid C star tensor category. And then the Homs in M sub A from A to B are going to be equal to the Homs in vex C from A to B tensor A. And so graphically, I can represent this as things that look like that. Okay? Now, what is the composition in my category going to be? Well, I can do F composed with G, and I can multiply them. I can take this little dangly that's corresponding to A, use the algebra multiplication on A, and so I stack the Homs and multiply, and this will be the definition of F composed with G. Okay? And you can directly check that the associativity of the algebra object gives you precisely the associativity of composition in this category. Okay? So this is a real category, and the point is that this kind of perhaps ad hoc seeming star structure is precisely what you need to induce a star structure on this category. Okay? So an arbitrary Hom, so I'll just tell you how that looks a little bit. An arbitrary Hom can actually be written as something like this. So I have A, B, and there's some C, so maybe direct sum over C, where these are Homs in C. And so I've just kind of used semi-simplicity here and rewritten it in a slightly more complicated way, but these spaces kind of are isomorphic. And now I can use that J to define a star structure here. So J, or a star of, we'll say, I'll actually label things now. I'll have alpha here, and I maybe have an F here, going to A, B, C, star. Well, I'm going to take the star of this morphism in C, pull the string up, and then apply J to this guy here. So this will be equal to alpha star, which goes now from B to C, A, and now I'll pull it up, and so I have C bar, and now I do J sub C of F. Okay, and you can check that the axioms that we've, or the definition of a star structure we've put here is precisely the one that makes this into a star category. So in other words, the star, a Hom from A to B, now the star maps it to a Hom from B to A, it's conjugate linear, and it's an involution, and it reverses the order of composition. So it does all the things that you want it to do. Yeah, and so maybe you can take that as a justification for this crazy definition. Okay, so great. So what have we done? We've taken an algebra, we've defined what it means to be a star algebra, and we've associated to it kind of this star category that's controlled by C. So let's look, before we move farther, and see what this category actually is in the case of when C is actually finite dimensional Hilbert spaces, and this vex C is actually just vector spaces. And it's something that we've all seen before. So if C is Hilbert FD, then we have vex C is just vector spaces. Okay, and so if we're given so that means that M sub A has objects equals finite dimensional Hilbert spaces. And what are the Homs? So Homs in M sub A from H, so I'll use H instead of little a's, I'll use actual H and K's because they're Hilbert spaces. Well, this, which again is given by this picture here, is nothing other than the bounded operators from H to K tensor with A. Okay, you can use kind of Frobenius reciprocity if you want to see this. And this is nothing other than isomorphic to the the matrices with entries in A. Dim K by dim H with entries in A. Okay? And so this is a perfectly good category that we're all familiar with. We have matrices with entries in A, and you can only compose the things where the Hilbert spaces match up, where the dimensions match up. Perfectly nice category. And if A is a star algebra, this has a canonical star structure, where you take the transpose of the matrix and you take the star of each entry. So A being a star algebra makes this category a star category. And you should think of this category as the category of free A modules, finitely generated free A modules. And so what we've done is just come up with a generalization of that, maybe using less fancy words, in an arbitrary thing. And so, again, we should think of this as kind of finitely generated free A modules because these are kind of finite objects. They're dualizable. And so, yeah, that's the idea. Okay, so you might ask, why are we doing all of this? And so we'll get to the kicker right now. So, what do I want to say? Yes, so a C-star category is a Banach star category such that the C star condition holds, and this is for all Hams F. They can go between any objects in my category. Okay, so maybe I should say a Banach star category is just like a Banach star algebra, but now they can have different endpoints, so I can only compose things where the source and the target match up, right? And then the Banach condition is just the norm of f composed with g is less than or equal to the norm of f times the norm of g, and the star just switches the order of things. So this condition is a C star condition, and in particular, it makes the endomorphism Hams, that's actually an algebra here. It makes that into a C-star algebra. Everyone can recognize this condition as precisely the C-star algebra condition. Okay, so this is the first condition, but now there's a more subtle condition which you really need to make the theory go, and it's that f composed with f has to be positive. So if f mapped from A to B, f composed with f star is in this C-star algebra end of A, and that has to be positive there. That does not follow automatically because so the C-star algebra end of A has its own set of positive elements. It has to know that when I've composed the Ham that goes outside of A and then come back with the star, that's supposed to be positive. So that's an additional condition that you need on this category. And so this is what you would call a C-star category, and it's what you should think of as a horizontal categorification of a C-star algebra. So these are related to C-star algebras the same way that groupoids are related to groups. Okay, so that's how you should think of these things. So.
May I just make a comment that axiom number 1 would be simpler if you just said the norm of f star f equals the norm of f star times the norm of f. But then would it...
well, it's not... yes, yeah, you're probably right.
That be sufficient? I mean, it would
actually, I think that's not sufficient because when I compose them the other way, I'm in a different C-star algebra. So since f star and f star f aren't in the same place, then it's actually not sufficient. Unlike the ordinary case of C-star algebras.
This one does imply that the norm of f equals the norm of f star.
Yes, but I'm not exactly sure, but my feeling is that might in fact be weaker, but I could be totally wrong about that. Yeah, I haven't thought deeply about that. That's a good point. Someone should sort that out. I'm not sure what the answer is.
And that star f, isn't f double star f?
F double star is f, yes. Yes. Okay. So now let me point out an observation. Being a C-star algebra is actually a property of a star algebra, and it's not additional structure. Being a C-star algebra is a property of a star algebra with no norm condition. Is a property of a star algebra not extra structure. So this is kind of counterintuitive, especially for those of you who maybe know the definition of a C-star algebra but don't know the whole theory. So when you define a C-star algebra, you say it's a Banach star algebra. So I automatically have to put this Banach structure on the algebra. Okay, well, it turns out that if you have a star algebra, being a C-star algebra is a property. So what you can do is define kind of a function from the elements to the real numbers by taking the spectral radius. And the star algebra is a C-star algebra if and only if that function is a C-star norm that satisfies all of the conditions. So if I give you a star algebra, being a C-star algebra is a property of that, and it's not an additional structure with all of this having to define a Banach norm on everything. So very similarly, being a C star category is a property of a star category. And not extra structure. So, what's the point of this? Well, now when I want to define a C star algebra object in a category, I'll just define it as a star algebra object whose category of right A modules is a C star category. And that's it. That's the definition of a C star algebra object. And yeah. So definition, A in vec C is a C star algebra, and I should mention that also W star algebra makes perfect sense. Being a W star algebra is also a property of a star algebra. It's one that's a C star algebra that happens to be a pre-dual of some Banach space. It has a pre-dual, right? And if it has one, it's unique, and so that's also a property. So you can ask similarly for a W star category, where you just ask all the Hom spaces to have pre-duals. And so it's a C star algebra, and I'm just going to, W star goes along for the ride. It's also just a property of a star category. If this category, eb sub A, is a C star or W star, respectively, category. Okay, and we notice that if we restrict to the case where C is trivial, this category of matrices with entries in A is going to be a C star or W star category if and only if A itself is a C star or W star algebra. And that's a straightforward exercise in matrix stuff. Okay? So this, in fact, it entirely generalizes the definition for the for C star and W star algebras. Okay? Cool.
A is not actually a C star algebra. It's not actually an algebra.
It's not actually an associative algebra. It's an associative algebra object in some category. But what we were able to do is take that algebra object and produce a star category and ask for that star category to be a C star category. And that's what it means to be a C star algebra.
Is there going to be an actual C star algebra arising out of this?
Well, so the C star category is, you can, just like you can take a groupoid and kind of make an algebra out of it by saying that things don't match.
Yeah.
And you can do the same thing here for this category of this C star category. You can make an algebra and then try to take some C star completion of that. So there are many C star algebras associated to it, but perhaps not like there's not a single C star algebra associated to this. Yeah, there's many associated to it. And indeed, I mean, you can take the endomorphisms of each of these objects, and that will be a C star algebra. So indeed, there's many C star algebras associated to this one object. Okay, just like for a normal associative algebra, all of these, if I put K by K matrices of A, those are all C star algebras, right? And so you have, in fact, have many C star algebras associated to just that one. This is a similar story here.
Those are Morita equivalent, aren't they?
Yes, and
Are these ones going to be in some sense too? Are they going to be
in some sense, but I'm not sure that they're actually Morita equivalent. Like, I'm not sure I don't think there's an invertible, there's not an obvious, at least, invertible bimodule between them in full generality. Because here, I mean, the Morita equivalent is kind of built into the definition, but here we're not amplifying by matrices, we're doing this funny thing where we're amplifying by objects in a category. So it's some kind of abstract version of that, but they're not necessarily going to be concretely Morita equivalent. Yep. Okay? Great. So what do I want to do next?
So are you saying that you have a potentially more general notion of Morita equivalence? Like two C star algebras are equivalent if you can realize them as endomorphisms of given objects in one of your setup such that they're related?
Possibly, yeah, that makes sense. I mean, you do have bimodules between each of the different C star algebras. You have bimodules; they're just not invertible. Like, I mean, so you could say that indeed maybe they're more generalized Morita equivalent if they're invertible by one of these bimodules coming from this, but it's not invertible, and so.
Already for non-unital C star algebras, the notion of Morita equivalence is more complicated.
Yeah, well, so already here, all of this required unital, and that was at the beginning. We haven't put any theory where there's non-unital, because if it's non-unital, this isn't even a category. This thing I defined, And so you have to start talking about, I forget the name of it, these categories without units. I don't know, they're kind of like magmas or something. Magma, horizontal magmas, or I don't know what they're called. But I also don't know anyone who thinks about those. So, but maybe this is a good reason to. I mean, if you're really interested in non-unital C-star algebras in a category, you're kind of forced to do that if you follow this approach. And I should mention that this definition that we come with at the end came after a long road of the wrong definitions. Like, this was not the first thing we're like, oh, you should just take the modules and ask that to be a C-star category. We were putting norms on all the spaces, and there were like all these norms we were keeping track of and all these really complicated conditions. And at the end, we realized, oh, you can just say it this way. And this turns out to be kind of a clean way to do it. Okay. Okay. So, now the next question is, now that we have a definition, where do these come from? Like, how do you actually get these things? How do you construct these things? And what are interesting examples that aren't just ordinary C-star algebras? Okay, so here's a theorem, and I'm not going to state the actual form of the theorem, but there's a, well, before I put the theorem, let's think about this category a little bit. So this is a category, but it actually has more structure than just being a category. It's a left C module category, which means that I can take this object, so the object is just the object of C, and I can tensor by something else in C. And I can actually pull my morphisms, and you should think in this picture, I can just add a string to the left, which has stuff in C, and I can put morphisms in there. And so this category actually has the structure of a left C module category. So it's the category of right A modules, of free right A modules, but it's also a left module category over C. And so it turns out you can go in the reverse. So if you have a C module category, a C star C module category, and you pick your favorite object, you can construct a C star algebra object uniquely that recovers that module category when you take its modules. So theorem, I'll say it as a canonical bijection, but in fact there's an equivalence of categories, but I don't want to bother defining what the categories are. So I'll say there's a canonical bijection between C star, and then I'll put in parentheses W star, although it kind of looks like I'm saying C star of W star, but this means C star or W star algebra objects in C. And cyclic C star or W star C module categories.
You mean vec C?
Yeah, so we have this kind of thing. We haven't quite decided if we want to call this an operator algebra object in C, even though it's actually an object in vec C. So perhaps I'll go with vec C. That's right. Okay, what do I mean by a cyclic C star C? So I mean you can take a big C star C module category, pick your favorite object, this will generate a cyclic module category. So somehow this kind of construction, once you've chosen your object, doesn't care about the rest of the module category. It only cares about the part of the module category generated by some object. And so what you do is if you have a C star algebra, you take its category of right A modules and you get a C module category. So conversely, if you have a C module category, if you pick your favorite object, you can do this kind of construction where you it's a little involved, especially via the definitions I gave you of these categories, but you can do a construction that produces a C star algebra object so that when you take its modules, you end up with the cyclic C module category you started with.
Wouldn't it depend on which object you take? Like
The identity. Take identity.
I see, but why is it a bijection? Wouldn't there be more really equivalent algebras that give the same module categories?
Yes, but I didn't tell you fully what cyclic means. Cyclic means you have to remember this kind of formal structure where the objects are objects of C, and you don't idempotent complete.
It determines specific algebra.
Yeah, exactly. So yeah, it's kind of a funny way, but we wanted to say it this way, and so we've defined cyclic in a way that makes this theorem true. Right? But morally speaking, yeah, you're right. I mean, you can have equivalent C module categories. But somehow the choice of object actually does determine the algebra you get here. So Morita equivalent. So two objects in the same indecomposable module category will give you Morita equivalent algebra objects upstairs, but they're not equal as algebra objects. And so cyclic means you've remembered your base point, and that kind of remembers the algebra. That's the idea here. Okay, So what this means is that if you want to construct C star and W star algebra objects, you should go look for C star or W star C module categories. So what's one place you would get such a thing? So examples, anytime I have a tensor functor, if f from C to D is a star tensor functor, so I don't need D to be a rigid C star tensor category at all. Maybe D is just a C star tensor category. Maybe it's the category of, maybe it's the category of Hilbert bundles over topological space or something. Like, it doesn't have to be any of these nice conditions, but if I have a star tensor functor, tensor is important here, then D has the structure of a C star C module category. Or W star if D happens to be W star. And so you can pick your favorite object and do this construction, and you end up with an operator algebra object in C. So in particular, if D is a tensor category, you pick the unit there. That's kind of a nice canonical object in D. You pick the unit, you do this construction, you get some kind of operator algebra object. So maybe some sub-examples where this has been, these algebra objects are actually quite interesting and have appeared in various places, particularly when studying analytic properties and things like this. So, so you can consider F is the forgetful functor from rep G, if G is a compact quantum group, down to Hilbert spaces, where I've just simply forgotten, I take my object in here, I've simply forgotten that there was an underlying Hilbert space, and I'm in this category here, and that's a tensor functor. So that makes Hilbert spaces, and really HilbFD, into a module category over this thing. So pick your favorite object in here, namely, I suggest picking the scalars, and you get an algebra object in C. Picking C yields it's actually a W star and C star. It's kind of in this funny world where it's what's called locally finite, and so it's both at the same, it's equivalent. So a W star algebra in C that behaves like the quantum group polynomial algebra. But in fact, it's a W star algebra. So it remembers somehow the actual quantum group structure. And indeed, it actually remembers this entire tensor functor because it's kind of, it's special. It's what we might call a factor object, a finite factor object. Yeah. So that's one example. And so another example is I can consider C as a C box times C op module category. Okay. And so what I get when I pick 1 in C as my favorite object, I get this object which we call the symmetric enveloping algebra object. Picking 1 in C, we obtain the symmetric enveloping algebra object. Okay. But before I give more examples, what do I mean by it remembers the quantum group structure, and why am I calling this the symmetric enveloping algebra object? Well, if we go back over to this situation, we have an obvious notion now of what it means to be a UCP map between algebra objects. Okay, we've kind of built that into the definition. So what was a UCP map between algebra objects here? Well, it's a map between algebras that on the amplifications, so on all of these other endomorphism algebras in the category, it's still positive, right? Well, we have a very nice notion of amplification in our setting, namely the endomorphism algebras in all of the other settings. So you can say a UCP map between algebra objects is one such that on the module category, it induces a positive map between C star categories. Okay, and so there's a nice natural notion of UCP map, and from that there's nice natural notions of UCP maps of analytic properties for certainly sufficiently nice W star algebras that kind of where this UCP map definition of things like amenability and property T makes sense. And if you apply that to these two examples, you recover the ordinary notions of analytic properties that we've seen for rigid C-star tensor categories here and for quantum groups here. So the moral of that side of the story is that maybe these properties that Pope and Voss defined for rigid C-star tensor categories can be thought of as properties of this W-star algebra object in the category C tensor C op. Okay? And for quantum groups, the analytic properties that we're familiar with for quantum groups are actually can be thought of as analytic properties of this W-star algebra object in this tensor category. Yes, definitely.
Questions on the quantum group side. One usually has to assume that the hard state is a trace to formulate all these things well. So don't you have to assume that here as well, or do you have
to formulate it really well? Yes, you do need that. That's a critical thing to really make good sense, especially with property T. But Hagerup and amenability actually makes sense using the CP multiplier notion. You can show that CP multipliers on the quantum group are actually the same thing as these CP multipliers on this module category. So for property T, it's hairy, at least as far as I know, because the different norms on the CP multiplier space, what's the convergence you're interested in. But for Hagerup and amenability, it's actually fairly straightforward. You just get a canonical bijection between CP multipliers and UCP maps, and it just goes through. Yeah. So, but that's the moral of the story, is that this kind of gives a better perspective on what those really mean, in some sense, because there's kind of a nice invariant way you can think about things here. Okay, but here everything is nice and perfect, and indeed this is kind of like a catch type sort of thing. Okay.
But still, I'm very much confused, because take SUQ2. If you view this on the quantum group side, it would be amenable.
Oh no. I mean
but it's
code
not
properties.
amenable.
These should be for discrete quantum groups, if that makes you feel better.
Yes, that's what I mean. So the dual of SUQ2 is amenable as a discrete quantum group, but very much not as a representation category. It's temporally leap.
Oh yes.
So what's the dictionary then?
So there's not a direct dictionary between C and the quantum group. They're totally different algebra objects. Oh yeah, you just put them, you have definitions for an algebra object. The two algebra objects are not related a priori at all. Yeah. No, there's not a way to go between the notion here and the notion here. There's separate notions that arise in different situations. Okay, yeah. I mean, maybe there is sometimes when you can go between these things, but there's no canonical thing that I know of. Okay. Although, if you take, so another thing you can do is you can take Hilb FD and think of it as a rep G tensor rep G op module category, just like you thought of it here. And when you do the construction there, you get something which is behaving like the Drinfeld double, and there you do have a connection between this one, as you established as you would expect from your work with Surin, right? So there is some kind of connection on the doubled side, but there's no obvious connection here. But somehow this kind of makes sense of definitions in each of the cases. They're kind of just properties for algebra objects in some sense. Okay, so that's kind of a nice notion. And you can put, so here's another nice example. Let's see, and I'm about out of time. But if F sends from C into BIM of N, okay, I can make the right N modules into a C module category. And when I take L2 of N, I can do this whole construction and I get an honest W star category. So somehow these were relatively small in the sense that the Hom spaces from any object to that A are still going to be finite dimensional, even though there's infinitely many objects. Here the Hom spaces are very big, and so you get really big, interesting kind of W star algebra objects from this kind of construction. And so there's a whole vast world of things to do. There's these small ones, there are these big ones, and it's very interesting to try to understand the interaction between them. But I'll finish here. Thank you.
Any more questions?
There is this abstract Tanaka duality by Doppler and Robertson. Do you think you can get any better understanding of that with this machinery?
So in some sense, yes. So in some sense, quantum group, so there's this notion of a finite factor object that you can define in a category, and this is kind of the same thing as tensor functors category to the bimodule category of some finite factor. And so in some sense, you can think of quantum groups as simply being finite factor objects in your category. In some kind of cool sense. So not just arbitrary finite factor objects, but finite factor objects over the scalars. If you take finite factor objects over some 2-1 factor, you get kind of tensor functors into bimodule categories of this thing. So in some sense, there is a kind of a generalization of this duality, but it's not necessarily a better understanding. But to me, I understand it better now when you think of things this way. But yeah, that's interesting to consider.
Any other questions? Okay, let's thank for